Hey everybody. Um, I wanted to say a few words about our team. Yeah, indeed, you got access to AWS infrastructure. I hope you got one. And actually, why I did that is that I actually wanted to support the community as well. I wanted to come to this school. Originally, there were no tickets, and I expected like there might be some issues with that. But luckily, we are here, and I'm here, and learn a lot. So we are Bioptic, a very small startup. We are just about 10 people. Not all of them on this slide, but you can get an idea of the people who we have. Like first of all, we have a person like our CEO is a tech guy who created YouTube Mobile. He literally ran it from 0 to 1, where there were just about 5 people. He joined Google that time and grew the product to 1 billion users. So then we got a previous director of data science from Novartis, Anna. And we also hired a VP of drug discovery of Atomwise. We got people from Neuralink, Apple, and a bunch of advisors. They are computational chemists by background, very known ones. They are professors and North Carolina University and Carnegie Mellon. And what I wanted to say is that we are like a pretty good defined team, but we still are looking for a good data generation pipeline for drug discovery. And that's actually because we only pivoted to drug discovery a year ago from now. So that's where tech people come to bio. And they think that this space should be dramatically changed over the next years. So that's why we joined and wanted to to make a change. We like building big products, and we have not figured out our final modality, but we at the moment work on small molecules. So as for small molecules, I will show you what we have as the only product at the moment. It's called Bioptic, obviously, and it's a search engine for small molecules where molecules are represented not by structure but by let's say potency. So it's kind of we can train a neural network to represent molecules with similar activity profiles so that they will be close to each other in the latent space of embeddings if two molecules most likely bind to the same set of targets. So with this idea, we started, and we are very good at retrieval systems. That's why we actually started with this. And we were able to scale this thing to n 40 billion easily. And it might be a bigger library if there is a need. But overall, the idea is like we need to search molecules not by structure, but by activity. So you can have a look at our website, Bioptic.io, so that you can get an idea what it is. And for the technical audience, of course, we got our first paper published, and you will also see the link in the website. I want to go through like a little bit to tell you like what we built and what kind of things you might also have today on your hackathon. First of all, we built this neural network which we call a target agnostic potency based small molecule search engine, right? So it is a single neural network that you can use for multiple targets. Basically, so you don't typically people train classification models like per target. Sometimes they do multitasking, but we haven't like clearly seen like success there and fair evaluation. That's what the most important part is. And we developed this multitask model. Then we benchmarked it against state-of-the-art models, including ChemProp, typical gradient boosting model. We should always check for it. And also, we have developed obviously an infrastructure that is very, very scalable. We got a very cool backend engineer who can scale things easily to any 40 billion. So this is the architecture. So first of all, there is a pre-training stage, and we represent smiles. We represent molecule as in smile string. We train a transformer in the Roberta style, basically. So we got about 160 million molecules from PubChem and random subset of enamine. And on this kind of diverse set, we pre-train our transformer on masked language modeling. So with about 15% tokens being masked, you kind of try to predict the token under the mask. After pre-training, we hope that the model learns some smiles grammar. We train our transformer on the real task, and here we take the last hidden layer of the transformer. We take the classification token as a separate embedding. Let's say not embedding, but a separate representation. We also take all other tokens as and aggregate them with max pooling and average pooling. Those are like kind of 3 different pooling types, and then we pass them through the linear layers and basically concatenate into a final embedding, so that every type of representation will have its own space in the embedding if there is a need to improve the quality. All of that we pass to the classification head and train on the multitask problem, where a lot of labels actually are missing. So we don't have a lot of ligand target pairs, and that's where we mask out. So it's generally a binary classification loss, but with masking. So, and to scale that, we built an infrastructure on AWS where we can once scan a big library. Let's say for enamine 40 billion, it was 8 nodes with 8 NVIDIA A100 GPUs, so 64 A100 GPUs in total. We scanned it for like about 5 to 7 hours. And once we got an index, now our users can search for the new compounds quickly. And the main goal here is to support users with different, like who work on different targets. Let's say they have some already found active compounds, and they pass them as queries. Let's say they have like 10 active compounds. They all pass them as queries. We run the search against this library and then aggregate, like, let's say, for example, a maximum of the scores among all queries. And that way we'll get the prediction for all the 40 billion library compounds. To be able to run the search quickly, and also not spend too much time on RAM, because there will be about 5 terabytes of RAM. Finishing? 5 terabytes of RAM, yeah. So we did it differently. We put all the data on the disks. There were 270 SSD disks connected to 27 machines, which are very cheap and small ones. Basically, we run a brute force search, brute force cosine similarity calculation. So it's not like the approximate nearest neighbors as people use nowadays, but that's because 5 terabytes of RAM will cost you like a big amount of money, right? We did it differently, and brute force allows us also to not tune any like complex parameters for approximate nearest neighbors algorithms, but instead just run the brute force and get a recall of 100%. Then we aggregate all the results in the database and give it to a user. So for the results, and basically the last piece I wanted to show is how we benchmarked our system. First of all, we selected 7 different targets. We consider them diverse. We did it this way. So first of all, we trained Bioptic till the last checkpoint, so that we don't cherry pick a model on the validation data set. First of all, about the validation data sets, that's super important. we test our system not like on random splits, not on scaffold splits, but there is a thing invented by an individual researcher called high splits, like basically hit identification data splits, where we separate training and test sets in such a way that there is at least 0.4 Tanimota dissimilarity. So those two sets should be very different from each other, and there is no any single point in the test set that will be closer to the train set by more than 0.4 Tanimota. So Tanimota similarity is a measure like of Morgan fingerprints, and it basically shows us structural dissimilarity, and that's super important to have a benchmark for the novel drug findings, and it's a hard one as well. And in this setup, we trained Bioptic till on each of the data splits, on each of these 7 data splits separately, so to show performance. We got some curve, and at the end, when it's saturated, we took a last checkpoint. Not for all targets, the model was saturated though, but we again have to stop it until, or otherwise it will overfit. So, and we trained on binding DB. It was about 3 million data points in general. And we here show that Bioptic can be as good as a typical classification model, although it's just pure transformer based on smile strings with just about 9 million parameters. And it shows great performance, like compared to Chemprop and gradient boosting model in just Morgan fingerprints. So, and it's so easy like to use. Like if you were onto Chemprop, you have to scan all the time the whole library. That will be very expensive for a new target. And here you just have index the data once and then run the searches, right? So that's super useful. And also we can have an active learning loop here where we get feedback from the wet lab. We can use those active compounds as queries and run the search again. So we don't need to fine tune, because basically fine tuning on 100 data points from the wet lab may not make any sense because you rather select those 100 as hard samples for the machine learning model, but you typically don't do that because you just want to progress on your program. So I think having an active learning loop with the search system is kind of working. And also we discussed that yesterday with Max from isomorphic labs. He also like still thinks that we cannot eliminate the MSA thing from the AlphaFold because it actually improves the quality where there's not enough data statistically to have the model on it. So guys, I want to finish. If you want to run a search for, and I mean 40 billion on 2.5 minutes, let me know. And yeah, and any questions? High splits. Yes, actually, you should see it available maybe sometime later in Polaris as well, I guess, because my teammate is contributing to Valence Labs team. I guess either there or another subspace. I actually don't know that part, but it should be available publicly soon. And also, there is a paper. It's called LOHI splitter. Find it like LOHA molecular splits. Well, guys, I hope I got you excited about transformers and smile strings. We can get some quality based on that. And good luck on the hackathon.